we're covering acid gas removal. And I'll go ahead and get started with the slide of the presentation. So a typical amine gas treating process consists of an absorber unit, the regenerator unit, and accessory equipment. In the absorber, a lean amine solution absorbs H2S and CO2 from the upflowing sour gas to produce sweetened gas stream as a product. The rich amine solution contains absorbed acid gases, and it's routed to the regenerator. And then it's a stripped overhead gas from the regenerator that's concentrated H2S and CO2. Absorption relies on the molecules to bind to the surface of certain solids. And after a certain time, the material must be regenerated to release the gas. Principles used to include the pressure absorption, or PSA, temperature absorption, TSA, and electric stream absorption, ESA. Your cryogenic removal uses a turbo expander, a gas turbine that is driven by the gas, and cools the decool gas to be removed. There's more on the for instance, the inlet gas in the compressor is pre-cooled. Cryogenic removal is most often used when the content of carbon dioxide is high, and it's typically around 50%. The membrane-based removal is based on certain materials that allow the acid gases, but not the hydrocarbons, to diffuse through the membrane. This procedure can be performed alone or in combination with the absorption liquid in the sulfur unit. And the H2O stripped gas stream is then fed to a Klaus process. And this is a multi-stage process with two main sections. A thermal section that fires the H2S with air or oxygen to produce sulfur dioxide and elemental sulfur, which is released when cooled. A catalytic section allows more H2S to react to SO2 with alumina or titanium dioxide to produce water and elemental sulfur. So this is the equation of the Klaus reaction. The Klaus process can recover 95 to 90%, 97% of the sulfur in the feed gases. A TerraGas treatment unit serves to reduce the sulfur content to below 215 parts per million, corresponding to a total sulfur recovery of 99.9%. More complex solutions can reduce the total sulfur down to 10 parts per million. Some important processes include SCOT, or Shell Klaus off-gas treatment, which removes SO2 by combustion with hydrogen over catalyst to produce H2S and water. H2S is recycled to the Klaus unit. Other solutions are the Bevan sulfur removal process, or BSR, and it's based on amine solvent and catalysts. Another part of the acid gas removal is dehydration. So this is either glycol-based scrubbers or based on pressure swing absorption, or PSA. Newer processes also use membranes. So membranes are used in other vessels. This is a glycol dehydration unit where you have your wet gas feed and glycol contractor with your rich glycol. You have a glycol pump. You have your rich flash where you get rid of flash gas and skim oil. You have a cross exchanger, then you have a glycol regenerator, and then you have a condenser. And you also have a reboiler. This is just another schematic of what the dehydration process looks like. The one on the right. We'll talk a little bit about mercury removal. Mercury is generally based on molecular shifts, and a molecular shift is a substance containing material with tiny pores to achieve a large surface area, such as activated carbon. The surface of the material allows certain molecules to bind by the surface tension, and the molecules can later be extracted and the shiv material regenerated by heating, pressure, and or purging with a carrier gas. And a molecular shiv is commonly cyclic with one active unit and one or more units in regeneration. So here's a schematic of the mercury removal, where you have your molecular shivs, like I mentioned to you about, with your inlet separation, with your stabilization, and you have your molecular shiv units. And then your inlet glass also goes to amine treating, which is molecular shiv dehydration. And then you go through additional molecular shiv units. And then you go through cryogenic separation, which is the demethanizer, deethanizer, depropanizer, and the debutanizer. Then I'll talk a little bit about nitrogen rejection. Excessive nitrogen is removed by a cryogenic distillation, and higher concentrations are removed by absorption with lean oil or other special solvent if a smaller fraction is detected. Cryogenic removal also permits production of helium if present as a valuable byproduct. So here's a schematic of the nitrogen rejection, where you have your nitrogen product, and then you also have your methane absorber. You have heat flash generation, so that's supposed to help you get rid of some of the nitrogen. And this also controls nitrogen in cells, the first flash production in the methane absorber. Then you have your ethylene glycol system, and you have your propane refrigeration as well. So now I'll talk a little bit about NGL recovery and treatment. Remaining NGLs are recovered from the gas stream in most modern plants by a cryogenic turbo expander-based process, followed by a fractionating process. This process leads to cooled NGLs through distillation columns called a deethanizer, depropanizer, and debutanizer to extract ethane, propane, and butane respectively, and leave a residual stream of pentane and higher hydrocarbons. The final step is to remove mercaptans, so these are smaller organic gases, if present in a sweetening process based on molecular source absorption, or catalytic oxidation such as Nerex mercaptan oxidation, or Sulfrex, which is the main difference in the type of catalyst. So I'll talk a little bit about fractionation. These plants separate high-value NGLs from natural gas production. These are usually blend components and refineries as feedstock in the manufacture of petrochemicals. So you have your gas inlet, and then you have your condenser with your ethane products. So this is the deethanizer. The depropanizer gets your propane product out, and your debutanizer separates your butanes out. And then it splits up to two different types of butanes, where you have your isobutane and you have your N-butane. If you look at the legend over here, the blue area represents steam, and then the green area represents a heat exchanger. So one thing I wanted to show you guys is that NGL is not the same as LNG. I wanted to show you guys this video. Let me share with you the sound.
The world's population is growing, and for many, living standards will continue to improve. As a result, global energy demand is expected to double by 2050 when compared to 2000. To help meet this demand, gas will form an increasingly important role. Natural gas is plentiful, and it's the cleanest burning fossil fuel. But some natural gas resources are in remote locations. Transporting the gas long distances by pipeline can be costly and impractical. The solution? We liquefy the gas by cooling it, which shrinks its volume for easier, economical, and safe transportation by ship. So how is liquefied natural gas produced? Natural gas extracted from the ground contains impurities, water, and other associated liquids. First, it is processed to clean it. It goes through a series of pipes and vessels where gravity helps separate the gas from some of the heavier liquids. Other impurities are then stripped out. The natural gas passes through a water-based solvent that absorbs carbon dioxide and hydrogen sulfide. These would otherwise freeze when the gas is cooled and so cause blockages. Next, any remaining water is removed, as this would also freeze. Finally, remaining lighter natural gas liquids, mainly propane and butane, are extracted to be sold separately or used as a refrigerant later in the cooling process. Traces of mercury are also filtered out. Now the purified natural gas, methane with some ethane, is ready to be liquefied. This happens in heat exchangers. A coolant, chilled by giant refrigerators, absorbs the heat from the natural gas. It cools the gas to -162 degrees centigrade, shrinking its volume by 600 times. This turns it into a clear, colorless, non-toxic liquid, liquefied natural gas, or LNG, that is much easier to store and transport. The LNG is kept in insulated tanks until it is ready for loading into a specially designed LNG ship or carrier. When the ship arrives at its destination, the LNG is transferred to a regasification plant where it is heated, returning it to its gaseous state. The gas is then transported via pipelines to customers, providing energy for homes and industry. Shell continues to help meet growing energy demand with cleaner burning natural gas.
So I'll talk a little bit about transportation now. So after field processing, the treated oil and natural gas is delivered through a huge complex transportation, pipeline transmission and distribution infrastructure, such as pipelines, marine, and rail. So there's also shipping and trucking. Liquefied natural gas, or LNG, is natural gas that's been cooled to a liquid state at about negative 260 degrees Fahrenheit for shipping and storage. The volume of natural gas in its liquid state is about 600 times smaller than the volume in its gaseous state in a natural gas pipeline. Where natural gas pipelines are not feasible or do not exist, liquefying natural gas is a way to move natural gas from producing regions to markets, such as to and from the US and other countries. Asian countries combined account for the largest share of global LNG imports. LNG export facilities receive natural gas by pipeline and liquefy the gas for transport on special ocean-going LNG ships or tankers. Most LNG is transported by tankers called LNG carriers in large onboard supercooled or cryogenic tanks. LNG is also transported in smaller International Organization for Standardization, or ISO, compliant containers that can be placed on ships and on trucks. And at important terminals, LNG is offloaded from ships and may be stored in cryogenic storage tanks before it's returned to a gaseous state or regasified. After regasification, the natural gas is transported by natural gas pipelines to natural gas-fired power plants, industrial facilities, and residential and commercial customers. Here's a chart I wanted to show you of the LNG imports and exports according to the EIA. So these are all imports in the United States, where it's stagnated past 2015, and the LNG exports have skyrocketed since 2015. And here, I also wanted to put the source of countries where we're getting the LNG imports. Majority of them are from Trinidad, 6% comes from Nigeria, 5% comes from France, and less than 0.4% comes from Canada. So I wanted to talk a little bit about storage. Because of large volumes and high pressure, natural gas is generally stored underground until it's ready to be transported to market. Depleted gas reservoirs, salt caverns, and aquifers are common storage facilities. So I know that we had a question about natural gas storage. So these are the common storage facilities, which are gas reservoirs, your salt caverns, and aquifers. I also wanted to show you the storage in our lower 48 states, where we can have about 3 trillion cubic feet of gas. There's also some sales gas specifications. The exact sales gas specification is specified by pipeline operators and distributors. Typical standard sales gas requirements use the following parameters. The volume is measured in standard cubic meters, and in 101 kPa, or standard cubic feet, it's 1 foot cubed, or 60 degrees Fahrenheit, and at 14.73 psi. The calorific value specifies the total amount of energy per unit generated during the combustion of the gas. The value is used to calculate the amount of energy delivered, and there are several values listed. Gross calorific value of gross heat combustion is the heat released when a specific quantity of fuel in the mixture with air is ignited. and the end products have returned to the initial temperature, normally at 25 degrees Celsius. And your specifications are typically 38.8 megajoules or 10.8 kilowatts, plus or minus 5% per standard cubic meter. In the US, it's 1030 BTU, plus or minus 5% per S standard cubic feet. Net calorific value or net heat of combustion is the net heat generated when the water vapor in the gas does not condense, so water forms during combustion, and can be 10% lower. So the Robb index measures the heating effect that a burner is exposed to during combustion. A higher value means that a greater thermal load on the burner. Different gases with the same Robb index will impose the same load on the burner, and excessively high value is a safety hazard, as it can lead to burner overheating and excess production of carbon monoxide during combustion. Calorific value and Robb index can be adjusted by blending gas from different sources, as well as addition or removal of nitrogen. The methane number is a value similar to the octane value for gasoline, and it's important when gas is used for internal combustion of engines, such as compressed natural gas. Hydrogen sulfide and overall sulfur content, both hydrogen sulfide and total sulfur, must be reduced. H2S is toxic as well as corrosive for the pipeline, as it forms sulfuric acid, and it should be kept as low as possible. Typical maximum values are 5 milligrams per standard cubic meter of H2S and total sulfur at 10 milligrams per standard cubic meter. And mercury should be kept below 0.001 parts per billion, which is a detectable limit. The goal is to limit emissions and to prevent damage to equipment and pipelines by mercury amalgamation, which makes aluminum and other metals brittle. So a dew point is a temperature below which some of the hydrocarbons in the gas can condense at pipeline pressure, forming liquid slugs that can damage the pipeline. The gas must also be clear of all water vapor to prevent the formation of methane hydrates within the gas processing plant or within the sales gas transmission pipeline. Particles and other substances must be free of particulate solids and all liquids to prevent erosion, corrosion, or other damage to the pipeline, and satisfy limits on carbon dioxide, nitrogen, mercaptans, and etc. First, additives go when a natural gas is intended for domestic use. Tetrahydrothiopene, or THT, is added so that the otherwise odorless natural gas can be detected in the event of a gas leak. The sulfurous smelling substance is added to equal a sulfur content of 4.7 milligrams per standard cubic meter. I'll talk a little bit about pipeline infrastructure. So they consist of driving compressors and pumps, valve stations, pig receive and launch facilities, where the pig is used for cleaning or inspecting the pipeline. A pipeline SCADA system and pipeline management system is required to control and operate the pipeline. At the pipeline terminal, the transport gas or liquid are fed from a high-pressure compressors and pumps. The pipeline terminal includes termination systems for the pipeline. A pig launcher and receiver is a minimum requirement, allowing insertion of a pipeline pigging device used to clean or inspect the pipeline on the inside. Essentially, it's a large chamber that can be pressurized and purged to insert and remove the pig or scraper without depressurizing the pipeline. The pig is often driven by pipeline flow, either directly or through a pump or turbine arrangement that also drives wheels that roll against the walls and mechanisms to rotate brushes and other scraping mechanisms. Intelligent pigs also contain instrumentation for remote controlling cameras. I'll talk a little bit about gas pipelines, compressor, and valve stations. One or more compressor stations are needed to keep the required gas flow in the pipeline. Internal friction will cause a pressure drop along the pipeline that increases with flow. Thus, starting pressure must be high enough to maintain a design capacity flow up to the final terminal. If this is not practically possible, the additional compressor stations are needed along the total length. Typical starting pressure is about 150 to 250 bar. The final pressure can be as low as 50 bar at the pipeline terminal end. As an example, about 150 megawatts in compressor power is required to transport 70 million standard cubic meters a day through the 1166 Wrangler pipeline with a starting pressure of 250 Orman range Yama. The initial section is 42 inches, which increases up to 44 at Sleipner, which is a little more than halfway. All of this is in the UK, by the way, where immediate pressure is 155 bar maximum. So there's also a 1200 Nord Stream pipeline from Russia to Germany, which has two parallel lines with the same dimensions, pressure and compression power, so each as line grid. So the block valve stations or valve stations are required to allow closure of off-flow at regular intervals to limit accidental release of gas in case of pipeline rupture. This will be determined by the maximum permissible released gas volume. A valve station is normally operated by the remote telemetry in addition to closing valve at least, contains pressure, temperature, and some level of flow measurement. These will feed back into the pipeline modeling system. Even if methane is lighter than air and will rapidly rise, other gases such as propane are present in up to 8% by volume and are heavier than air. They will sink and rapidly create a large volume of combustible gas mixture. In cases where multiple producers and pipelines feed into a larger pipeline grid, the pressure balancing to maintain a required flow and absorb contractual volume allocations back into the individual production sites and presents additional challenges for the pipeline balancing system. So I'll talk about pipeline management, control, and safety. So pipeline management is used to maintain operation and integrity for the system. It's usually handled by a SCADA system, which interfaces with remote locations and collects data. And control valves and process set points. The pipeline management system may include functions such as a supervisory control to oversee the operation of the entire pipeline system, demand forecasting to model demand of the coming days across the system based on parameters such as contractual volumes, forecasts from consumers and producers, and meteorology to determine the necessary supply rates and corresponding pressures at various points in the network. Since the transport delay can be considerable during the off-peak season, delays can be compensated by pre-charging the line in anticipation of increases or allowing the pressure to be bled off if a reduction is expected. So pipeline modeling models the entire pipeline system to account for the pressure, temperature, and flow at major checkpoints. Based on this model, the management system can perform pressure balancing to make certain that pressure set points are correct to meet the demand forecasts and avoid potential overload conditions. Production allocation, which ensures that producers are able to deliver their contractual volumes into the network. Leak detection, which compares actual measured data against dynamic data presented by a model. A discrepancy indicates the leak or falling measurement. Simple liquid systems only calculate basic mass balance, while an advanced modeling system can give more precise data on size and position of the leak within a certain response time. A pig or scraper tracking is used to track the position of the pig within the pipeline, both from the pig detection and instruments in the pressure gulf are caused by the pig in the pipeline. In case of liquid pipelines transporting batches of different products, a batch transfer system is needed. Based on the information of which the product is injected in the pipeline and gravity measurement at the receiving end, it is possible to sequentially transfer different products such as gasoline and diesel in the same pipeline. So depending on the product characteristics, there will be an interface section between the two products as it widens as the product moves along the line. This off-spec product must be discarded at the receiving end to avoid product degradation. It is often disposed by mixing with larger volumes of low-grade fuel products. The system is often used with countrywide refined product distribution to terminals. Safety systems are used as for other process plants to ensure that systems shut down in the case of malfunctions or out-of-bound conditions. A highly reliable system that is needed to maintain production against overpressures and manage shutdowns. The strategy used by normal safety system to isolate and deep pressure or simply fail-safe to condition often cannot be applied to pipelines due to large volumes of product in the pipelines. And simply opening or closing a valve would potentially cause overpressure conditions and overload safety devices such as flares. HIPS monitors and executes these responses in a specific sequence. So now the next part I'll talk about is downstream. What exactly is that? So downstream is the sectors of refining petroleum crude oil and the processing and purifying of raw gas, supply and trading, as well as the marketing and distribution of products derived from crude oil and natural gas. The downstream sector reaches consumers through products such as gasoline or petrol, kerosene, jet fuel, diesel oil, heating oil, fuel oils, lubricants, waxes, asphalt, natural gas, and liquefied petroleum gas, or LPG, as well as hundreds of petrochemicals. Now, you real petroleum refining that's simplified.
And free, down a better down, free down, hit free here, free fire down, get free down, get free down, make that free, hit free here, free down, free, make that free.
That's right. TurboTax Free Edition is free. Free.
Refining begins with a process called distilling. After oil is superheated, it becomes vapor. The vapor is fed into the distillation unit. As it rises and cools, the vapor turns back into a liquid. Using stacks of trays, the liquid is easily collected and separated by weight. The lighter and medium weight liquids require less processing before they're ready to be used in cars and trucks. The heavier liquids need more processing to become useful. A process called cracking is used to maximize the usefulness of heavy oil. Heavy oil has long strings of carbon and hydrogen molecules. Using a catalyst, these molecules can be broken into smaller chains, transforming the heavy oil into lighter, more valuable fluids. Reforming is a process that increases the amount of gasoline produced from crude oil. One of the products separated in the distilling process is a liquid called naphtha. The number of carbon atoms in naphtha is about the same as the number found in gasoline, but their structure is more complex. Reforming rearranges the naphtha molecule, turning it into a usable, gasoline-like molecule. Blending is a process of mixing different refinery products to make finished petroleum fuels. Gasoline, for example, is blended to achieve octane standards, creating the grades of gasoline you see at the pump: regular, mid-grade, and premium, that are necessary to meet the needs of specific engine types. Treating is a process used to produce cleaner gasoline, which helps protect both the environment and our health. Gasoline molecules contain impurities like sulfur that can be removed. When the molecules are heated and come in contact with a special catalyst, a chemical reaction occurs that strips the sulfur away. These sulfur compounds are used as fertilizers and in pharmaceuticals. Nothing goes to waste in a refinery.
For my meal kit delivery, I chose the vegetarian box, and the meals that...
So that is a basics of refining. Let's talk a little bit about oil refining. Crude oil is a mixture of different hydrocarbon components. Each component has its own size, weight, and boiling temperature. Refineries convert crude oil into a variety of useful products through a number of different processing units using heat and pressure to separate the products. And I won't go into every single one, but this is just giving you a history of refining, where in 1862 you had atmospheric distillation. It was to produce kerosene. Then you had vacuum distillation. Then you had thermal cracking. You had sweetening, thermal reforming, hydrogenation, coking, solvent extraction, solvent dewaxing, catalytic polymerization, catalytic cracking, viscid breaking, alkylation, isomerization, fluid catalytic cracking, deasphalting, catalytic reforming, hydrosulfurization, inhibitor sweetening, catalytic isomerization, hydrocracking, catalytic dewaxing, and residual hydrocracking. So this shows you the range of ranges of processes that are in refining, and we can go on and on about all of these processes. So fractionation is the separation of crude oil and atmospheric vacuum distillation towers into groups of hydrocarbon compounds of different boiling point ranges. They're called fractions and cuts. The conversion process just changes the size and or structure of hydrocarbon molecules. These processes include decomposition or dividing by thermal or catalytic cracking, unification or combining through alkylation and polymerization, and alteration or rearranging with isomerization and catalytic reforming. Treatment processes are intended to prepare hydrocarbon streams for additional processing and to prepare finished products. The treatment may include the removal or separation of aromatics and naphthalene, as well as impurities and undesirable contaminants. The treatment may involve chemical or physical separation, such as dissolving, adsorption, or precipitation using a variety of combination of processes, including desalting, drying, hydrosulfurizing, solvent refining, sweetening, solvent extraction, and solvent dewaxing. Formulating and blending is the process of mixing and combining hydrocarbon fractions, additives, and other components to produce finished products with specific performance properties. Other refining operations include white ends recovery, sour water stripping, solid waste and wastewater treatment, process water treatment and cooling, storage and handling, product movement, hydrogen production, acid and tail gas treatment, and sulfur recovery. And this all comes from the OSHA website. There are some auxiliary processes when it comes to refining. You've got steam and power generation, process and firewater systems, flows and release systems, furnaces and heaters, pumps and valves, supply of steam, air, nitrogen, and other plant gases, alarms and sensors, noise and pollution controls, sampling, testing, and inspecting, laboratory control room maintenance, and administrative facilities. So this is just giving you a separation of what kind of processes are there. For the fractionation process, you have atmospheric distillation and vacuum distillation. They're meant to separate fractions and separate without cracking. Then you have the conversion process, such as the decomposition, where you have catalytic cracking, you have coking, and you have hydrocracking. And this is meant to upgrade gasoline, convert vacuum residuals, and convert to lighter hydrocarbons. Then you have hydrogen steam reforming, steam cracking, and vice breaking. This is meant to produce hydrogen, crack large molecules, and reduce viscosity. Then you have the unification process and conversion. So you have alkylation, grease compounding, polymerizing, and this is to unite olefins and isoparaffins, combine soaps and oils, and unite two or more olefins. And then you have catalytic reforming, where it's to upgrade low octane naphtha. And you also have isomerization, which is converting straight chain to branches. And then for the treatment process, you have amine treating, deslating, drying and sweetening, for fuel extraction, hydrosulfurization, hydrotreating, phenol extraction, solvent deasphalting, solvent dewaxing, solvent extraction, and sweetening. And for all of these, it's meant to remove acid contaminants, remove H2O and sulfur compounds, upgrade or mid-distillate lubes, remove sulfur contaminants, remove impurities and saturate hydrocarbons, improve viscosity and index color, improve asphalt, remove asphalt, remove wax from loop stocks, separate unsaturated oils, and remove H2S and convert mercaptan. So here are some products from refining. So the light products, you got liquid petroleum gas or LPG, gasoline, and then naphtha used as a solvent or a paint thinner. For medium products, you got kerosene and related jet aircraft fuels, and you have diesel fuel. For heavy, you've got fuel oils, lubricating oils, paraffin wax, asphalt and tar, and petroleum coke. I'll talk a little bit about integrated and independent refiners. The integrated refiners, you got companies such as BP, ExxonMobil, Chevron, Shell, and Total. And the independent ones, they have no exploration and production operations. So this is strictly midstream and downstream. This is Valero, Tesoro, and Seneca. Wanted to show you a few charts for supply and trading. So this is the distribution of proved reserves from 1999, 2009, and 2019. For 2019, you'll notice that the Middle East and then Commonwealth and states. So Russia, for example, these two are the highest in terms of supply and trading of proved reserves. Wanted to show you the prices as how they've changed over time. Gas prices, especially heavy have declined over time. And then you'll notice the other gas prices are pretty much on trend. Henry Hub is represented in red. This is the exception of Japan LNG. Everything else has gone down. So we're also going to the minds of traders, and they might consider trading in natural gas. And there are a few reasons why. You have clean fossil fuel demand, with inflation and weak US dollar hedging, and with portfolio diversification. And I'll explain each three. For the clean fossil fuel demand, natural gas is considered much more environmentally friendly than petroleum or coal, burns cleaner and produces fewer carbon emissions. Natural gas is lighter than air. In case of a leak, it will dissipate, which gives it a safety advantage over gasoline. For the inflation, investing in natural gas is a way to bet on a weak US dollar and higher inflation. Natural gas is priced in US dollars, so the performance of the world's largest economy can impact its price. The US Federal Reserve Bank has kept interest rates low and the US dollar weak for many years. The weak dollar could stroke inflation concerns. Since there is a limited supply of natural gas, the price of commodity could benefit from the fears of inflation. You also have portfolio diversification. Investing in natural gas along with other commodities is a way to diversify an investment portfolio. Investors seeking true asset class diversification should consider putting a portion of their investable assets into a basket of commodities, including natural gas, other energy commodities, metals, and agriculture. Natural gas is consumed primarily in the pulp and paper, metals, chemicals, petroleum refining, stone, clay, glass, plastic, and food processing industries. And these businesses account for over 84% of all industrial natural gas use. Wanted to show you the production and consumption, where you have North America producing and the Commonwealth of States producing the most amount of natural gas. But the consumption by region, you'll notice that's also North America. And you have Europe, as well as the Commonwealth and States. Asia Pacific has been growing quite a bit. I'll talk a little bit about natural gas growth. So the consumption increased by 78 billion cubic meters, or 2%, well below the exception seen in 2018. The share of the gas is primarily energy rose to a record high of 24.2%. Increases in gas demand were driven by the US and China, while Russia and Japan saw the largest declines. Gas production grew by 132 BCF. Two-thirds of this increase Australia, and China. The gas trade expanded at a rate of 4.9%. Its 10-year average, driven by a record increase in liquefied natural gas. LNG supply growth was led by the US and Russia, with most incremental.
सर अभी रजिस्ट्रेशन सर नहीं हुआ सर.
European LNG imports rose by more than 2/3. A little bit about some technologies such as natural gas fuel cells. This is the ability to generate electricity using electrochemical reactions as opposed to combustion of fossil fuels to generate electricity. So a fuel cell works by passing streams of fuel as iron oxidants over electrodes that are separated by an electrolyte. And this produces a chemical reaction that generates electricity without requiring the combustion of fuel or the addition of heat, as it's common in the traditional generation of electricity. When pure hydrogen is used as fuel and pure oxygen is used as the oxidant, the reaction that takes place within the fuel cell produces only water, heat, and electricity. And in practice, fuel cells result in very low emission of harmful pollutants and in generation of high quality, reliable electricity. So the reason for the fuel cells, you have clean electricity, distributed generation, dependability, and efficiency. Fuel cells provide the cleanest method of producing electricity from fossil fuels, while a pure hydrogen, pure oxygen fuel cell produces only water, electricity, and heat. Fuel cells in practice emit trace amounts of sulfur compounds and very low levels of carbon dioxide. However, carbon dioxide produced by fuel cell use is concentrated and can be readily reached, as opposed to being emitted to the atmosphere. And then fuel cells can come in extremely compact sizes, allowing for their placement wherever electricity is needed. This includes residential, commercial, industrial, and even transportation settings. For the dependability portion, fuel cells are completely enclosed units with no moving parts or complicated machinery. This translates into a dependable source of electricity, capable of operating thousands of hours. And in addition, we're quiet and safe sources of electricity. Fuel cells also do not have electricity surges, meaning that they can be used where there is a constant, dependable source of electricity that's needed. And for the efficiency standpoint, fuel cells convert the electricity stored within fossil fuels into electricity much more efficiently than the traditional generation of electricity using combustion. This means that less fuel is required to produce the same amount of electricity. The National Energy Technology Laboratory estimates that, used in combination with natural gas turbines, fuel cell generation facilities can be produced and will operate 1 to 20 megawatt range at 70% efficiency, which is much higher than the efficiencies that can be reached by traditional generation methods within the output range. So here are some schematics of distillation, where you have atmospheric distillation in the schematic, and then you have vacuum distillation on the right. Then you have solvent distraction and dewaxing. So this is an aromatics extraction schematic, where you have extract solvent evaporators, you have rotating disc contractors, and you have a raffinate solvent evaporator. Now I'll talk a little bit about thermal cracking. Because of the simple distillation of crude oil products and amounts and types of products are not consistent with those required by the marketplace, subsequent refinery processes change the product mix by altering the molecular structure of the hydrocarbons. One of the ways of accomplishing this change is through cracking, which is a process that breaks or cracks heavier, higher point petroleum fractions into more valuable products such as gasoline, fuel oil, and gas oils. Catalytic cracking, it breaks complex hydrocarbons into simpler molecules in order to increase the quality and quantity of lighter, more desirable products and decrease the amount of residuals. This process rearranges the molecular structure of hydrocarbon compounds to convert heavy hydrocarbon feedstock into lighter fractions, such as kerosene, gasoline, LPG, heating oil, and petrochemical feedstock. So similar to thermal cracking, except that catalysts facilitate the conversion of heavier molecules into lighter products, the use of a catalyst or a material that assists the catalyst reaction but does not take a part in it, and the cracking reaction increases the yield of improved quality products under much less severe operating conditions than in thermal cracking. So here's a schematic of a fluid catalytic cracking process. We have the refrigerator, we have the refractor or the separation vessel, and we have the fractionator, and then you have the slurry setter. For hydrocracking, there's a two-stage process combining catalytic cracking and hydrogenation. One of the heavier feedstocks are cracked in the presence of hydrocarbon to produce more desirable products. The process employs high pressure, high temperature, a catalyst, and hydrogen. And the hydrocracking is used for feedstocks that are difficult to process by either catalytic cracking or reforming, since these feedstocks are characterized usually by high polycyclic aromatic content and or high concentrations of the two principal catalyst poisons, sulfur and nitrogen compounds. So this is the hydrocracking process schematic where you have multiple stages, and a high pressure separator, and then you have some fractionation that's happening at the end. Catalytic reforming. That's used to convert low-octane naphthas into high-octane gasoline blending components called reformates. Reforming represents a total effect of numerous reactions such as cracking, polymerization, dehydrogenation, and isomerization taking place simultaneously. Depending on the properties of naphtha feedstock, olefin, naphthalene, and aromatic content, and catalyst used as reformates can be produced with very high concentrations of toluene, benzene, xylene, and other aromatics, useful in gasoline blending and petrochemical processing. Hydrogen, a significant byproduct, is separated from the reformate for recycling and the use of other processes. Then we have catalytic hydrotreating. Hydrogenation process is used to remove about 90% of contaminants such as nitrogen, sulfur, oxygen, and metals from the liquid petroleum fractions. These contaminants, if not moved from the petroleum fractions as they travel through the refining processing units, can have detrimental effects on the equipment, the catalyst, and the quality of the finished product. Typically, hydrotreating is done prior to processes such as catalytic reforming, so that the catalyst is not contaminated by the untreated feedstock. Hydrotreating is also used prior to catalytic cracking to reduce the sulfur and improve product yields, and to upgrade the middle distillate petroleum fractions. Into finished kerosene, diesel fuel, and heating fuel oils. In addition, hydrotreating converts olefins and aromatics into saturated compounds. So we'll talk a little bit about isomerization. This converts N-butane, N-pentane, and N-hexane into respective isoparaffins of substantially higher octane number. The straight chain paraffins are converted to their bloodstream counterparts, whose component atoms are the same but arranged in a different geometric structure. Important for the conversion of N-butane into isobutane to provide additional feedstock for alkylation units and the conversion of pentanes and hexanes into higher balanced isomers for gasoline blending. Isomerization is similar to catalytic reforming in that the hydrocarbon molecules are rearranged, but unlike catalytic reforming, isomerization just converts normal paraffins to isoparaffins. For polymerization is the process of converting light olefin gases, including ethylene, propylene, butylene, into hydrocarbons of higher molecular weight and a higher octane number that can be used as gasoline blending stocks. Polymerization combines two or more identical olefin molecules to form a single molecule with the same elements in the same proportion as original molecules. And polymerization may be accomplished thermally or in the presence of a catalyst at lower temperatures. For alkylation, it combines low molecular weight olefins with isobutene in the presence of a catalyst, either sulfuric acid or hydrofluoric acid. The product is called alkylate and is composed of a mixture of high-octane branched-chain paraffinic hydrocarbons. Alkylate is a premium blending stock because it has exceptional anti-knock properties and is clean burning. And the octane number of the alkylate depends mainly upon the kind of olefins used upon operating conditions. So we'll talk a little bit about sweetening and treating. Contaminants such as organic compounds containing sulfur, nitrogen, and oxygen, dissolved metals and inorganic salts, and soluble salts dissolved in emulsified water are removed from petroleum fractions or streams. Petroleum refiners have a choice of several different treating processes, but the primary purpose of the majority of them is the elimination of unwanted sulfur compounds. A variety of intermediate finished products, including middle distillates, gasoline, kerosene, jet fuel, and sour gases, are dried and sweetened. Sweetening, a major refinery treatment of gasoline treats sulfur compounds to improve the color, odor, and the oxidation stability. And sweetening also reduces concentrations of carbon dioxide. I'll talk a little bit about unsaturated gas plants. They recover light hydrocarbons from wet gas streams from the FCC and TCC, and delayed coker for fluid catalytic cracking and thermocatalytic cracking, and delayed coker overhead accumulators or fractionation receivers. In a typical gas plant, the gases are compressed and treated with amine to remove hydrogen sulfide either before or after they're sent to a fractionating absorber, where they mix into a countercurrent flow of debutanized gasoline. The light fractions are separated by heat in the boiler, and the off gas is sent to a sponge absorber, and the bottoms are sent to a debutanizer. And then the portion of the debutanized hydrocarbon is recycled, with the balance sent to the splitter for separation. The overhead gases go to a depropanizer for the use of alkylation unit feedstock. For saturated gas plants, this will be the last slide I'll cover for today. They separate refinery gas components for including butanes for alkylation, pentanes for gasoline blending, LPGs for fuel, and ethane for petrochemicals. Because the saturated gas process depends on the feedstock and product demand, each refinery uses different systems and usually absorption fractionation or straight fractionation. In the absorption fractionation, gases and liquids from various refinery units are fed into an absorber deethanizer, where C2 and lighter fractions are separated from heavier fractions and by lean oil absorption and removed for use as fuel gas or petrochemical feed. The heavier fractions are stripped and sent to a debutanizer, and the lean oil is recycled back to the absorber deethanizer. C3 and C4 are separated from pentanes in the debutanizer, scrubbed to remove hydrogen sulfide, and fed to a splitter where propane and butane are separated. And in the fractionation of saturated gas plants, the absorption stage is eliminated. So we'll talk about other refinery technologies such as heat exchangers, coolers, and process heaters, steam generation, pressure relief and flare systems, wastewater treatment, cooling towers, gas and air compressors, marine, tank car and tank truck loading and unloading, turbines, pumps, piping and valves, and tank storage. And we'll start tomorrow with the gas end users and sectors. I will stop for today, and I'm open to any questions you may have for me.
Hello, ma'am.
Yes.
Thank you for a wonderful lecture, ma'am. Ma'am, actually, I want to know if a natural gas reservoir is identified, how the first well is drilled with what are all the parameters they are taking into consideration and they are drilling first well. And once the first well is drilled, how they are developing the field.
That's a really good question. You need to make sure that the gas is producible and it's economic, which is the determination of drilling the first. And then once you figure out the style and how that well is fractured and how that well, then you can figure out how to develop the rest of then you can figure out how to develop the rest.
Ma'am, actually, can you say again? Hello?
Yeah, I was going to say, first, it depends on the determination of natural gas. First of all, is you need to figure out whether if it's economic to drill the well. If it's economic, to drill the well. If it's economic to drill the well, and if you completed it with gas, you also need to figure out the optimum field.
Ma'am, actually, it was breaking. I couldn't able to hear you properly.
I meant to say you need to look at the economics of the well.
Okay, ma'am.
And then I said that you need to look at optimal well spacing, which is another economic to develop the entire field.
Okay, ma'am. Thank you, ma'am.
For sure, I don't think there are any questions.
Ma'am, what is SCADA system? SCADA?
SCADA is the automation to look at some of the data on the computer in time. If there are any more questions.
Hello, ma'am. Actually, today you told about some standard temperature and pressure. So, ma'am, generally, what is the standard temperature and pressure to measure a 1 cubic feet volume of the gas?
Oh, I can go back to that slide. So the standard 60 degrees Fahrenheit and 14.7 degrees 25 C and then 101.325 kilos.
25 degrees Celsius temperature and pressure will be 14.7.
101.3 For sure, I don't think there are any more questions.
Okay. Okay, then we can conclude the session here. If anyone are having any doubt, then they can reach out to you, or else they can drop text message in WhatsApp group, or they can email us also.
Awesome.
Yeah. Okay, ma'am. Thank you so much.
Sure thing.
Yes.
Thank you, ma'am. Thank you for wonderful lecture.
Nice
Thank
day.
you.
Thank you so much, participant. The session is over. Everybody can leave the meeting.